In the last lecture, we acquainted ourselves with the concept of transform diagrams and how they help us in writing down the equations of performance of a network in the Laplace transform domain. We took up this particular example where the switch S is closed at t equals 0 and we are asked to find out this current I. And then taking note of the initial current in inductance to be 2 amperes, we replace that initial condition in the current by an equivalent voltage source in the transform diagram and we establish this transform diagram. As I mentioned in the last class, once we have the transform diagram, that can be analyzed in almost the same lines as what you would do in the case of DC circuits, writing down the various equations. We took up in the last class the loop current method for the solution of this network. We may as well use the node voltage method. We can use superposition technique, we can use Thevenin's theorem, whatever, all the whole gamut of techniques that are available, that is available for solution of DC circuits or AC circuits can be applied to the transform diagrams as well. Just for the sake of illustration, let me solve the same circuit by the node voltage method. Suppose I take this as the datum node, and if I solve for this node voltage, then I can find out the current in the 6 ohm resistor by dividing that voltage by 6. Therefore, I would like to use the node to datum voltage method. This is the node voltage to be solved for. Suppose this is the node 2, the value of this node voltage with reference to the datum is 10 by S, that is already known, and suppose I call this node 3, the voltage of node 3 to the datum is already known. So, our aim is to write the node equations to solve for V1. So, there is only one unknown node voltage, therefore, let us say V10 of S times the sum of the admittances connecting that node. One admittance is, this is generalized admittance I am talking about, the impedance is 3, therefore, the admittance is 1 by 3. The admittance of this combination, this whole entire branch, the impedance is S plus 2, therefore, the admittance is 1 over S plus 2 plus the impedance of this is 6, generalized impedance, the admittance is 1 by 6. That is the self node admittance of node 1. Therefore, the mutual terms you have to take V20 of S and the admittance connecting nodes 1 and 2 is 3, therefore, 1 by 3, therefore, that is the coupling term that you are having. Further, you also have a coupling term with reference to 30 of S. So, the admittance joining nodes 1 and 3 is 1 over S plus 2. So, for 1 over S plus 2, this must be the sum of the currents entering node 1 through the various current sources. In this particular example, there is no such current source, therefore, it is 0. Now, in this equation, the only unknown is V10 of S, because V20 of S is known, that is equal to 10 by S. V30 of S is also known, since the polarity is plus with the 0 has positive polarity with reference to 3, V30 can be written as minus 2. On substitution of these values for V20 and V30, we can get V10 of S. V10 of S can be calculated and shown to be 6 times 4S plus 20 divided by 9S times S plus 4. But we are interested not in V10 of S, but the current in this 6 ohm resistance. Therefore, IFS is obtained by dividing V10 of S by 6, and when you do that, this becomes 4S plus 20 divided by 9S times S plus 4. 9S times S plus 4. This is exactly the same expression that we got for the current IFS using loop current methods, and once we have got up to this point, the further work is the same as what we have done in the case of loop current method. So, I will not do that. So, from this you can get I of t. The point is that once you have the transform diagram, you can analyze the transform diagram by any one of the known techniques that are available to you in the whatever you do in the case of DC circuits can be applied to these transform diagrams as well, except in terms of resistances you have generalized impedances, except in terms of type DC voltage sources you have transformed voltage sources, instead of DC current sources you have transformed current sources. So, everything is in terms of S, but otherwise the principle, the technique is the same. Now, next question that we would like to ask ourselves is how to deal with mutual inductance. We have so far addressed ourselves to finding out the generalized impedances of R, L and C elements. What do we do when we encounter mutual inductances? So, suppose I have two coupled coils having self inductances L1 and L2. These are the dot points and they have a mutual inductance M between them, and let me say the voltages and the currents of the two coils are indicated as follows, as given here. Then in time domain the equations of performance of this mutually coupled pair of coils is V1 equals L1 di1 dt plus M di2 dt, because the two currents, both the currents enter the dot points, therefore the sign of the mutually induced EMF is the same as the self induced EMF, therefore this is plus, that is also plus. V2 likewise is M times di1 dt plus L2 times di2 dt. These are straightforward standard equations governing the behavior of a pair of coupled coils, which you know. Now, when we transform these equations, term by term you transform. So, V1 will have Laplace transform V1 of S. When you transform this, this will be L1 times S times I1 of S minus I1 0. That is the Laplace transform of L1 di1 dt. Similarly, the Laplace transform of M di2 dt will be M times S times I2 of S minus I2 0. Second equation will be V2 of S M times S times I1 of S minus I1 0 plus L2 times S times I2 of S minus I2 0. So, this is a straightforward application of the transforming these equations. Now, we have to draw a transform diagram which depicts these equations. So, what you have now is V1 of S is L1S times I1S plus MS times I2 of S plus minus L1 I1 0 minus M I2 0. Therefore, if I have in the transform diagram for the first coil, V1 of S is the transformed voltage, terminal voltage of the coil, and the coil has a self inductance L1 and it has got a generalized impedance L1 of S. This is self impedance of the first coil, and you have two sources, voltage sources representing the initial currents in the inductors. Therefore, this is L1 I1 0. Suppose I1 0 I write as rho 1 and I2 0 as rho 2 to simplify my notation. So, L1 rho 1 and minus M I2 0, therefore, you have another term M rho 2. So, you have two voltage sources representing the initial currents in the inductors, and The second coil likewise will have a representation like this, where V 2 of s is the terminal voltage and the current is I 2 of s, and the Laplace transform of the current here is I 1 of s, L 2 of s, and then here you have once again minus m I 1 0, L 1 of s minus I 1 0, that is m times rho 1, and here you have L 2 times rho 2. In addition, we have a coupling impedance ms here. So, that means once we have write down this equation, the transform diagram in this fashion, we say the voltage, terminal voltage V 1 of s of this coil is I 1 of s passing through L 1 of s will create a drop L 1 of s times I 1 of s. In addition, I 2 flowing to this coil will have a mutually induced voltage here, whose Laplace transform is ms times I 2 of s. So, you have not only L 1 of s, L 1 s times I 1 of s plus also ms times I 2 of s, L 1 of s I 1 of s plus ms times I 2 of s. In addition, representing the initial currents in the inductors, we have two voltage sources. Likewise, the same situation is there in the second coil also. This is very similar to what you do in the case of steady state circuit analysis, AC circuit analysis, where instead of the self inductance is represented as an impedance j omega L 1. The mutual impedance is j omega m. So, instead of j omega we have s, otherwise it is exactly the same that the situation that you have in the case of AC circuits. Now, you may as well think of replacing the initial currents through current sources. So, if you do that, you can write this equation in this form. You can write V 1 of s, V 1 of s you can write as L 1 s times I 1 of s minus rho 1 by s. So, instead of writing minus L 1 rho 1, I can write L 1 of s times minus rho 1 by s. So, this term here is put in this form plus ms times I 2 of s minus rho 2 by s, and you can write V 2 of s exactly going in the same method, ms times I 1 of s minus rho 1 by s plus L 2 of s times I 2 of s minus rho 2 by s. That is what we are having. So, if you look at these two equations, you can represent them in this fashion. You can have a current source here. So, let this current source be of strength rho 1 by s. So, the current in the actual inductor here is I 1 of s minus rho 1 by s, and that current passing through L 1 of s will set up a voltage drop L 1 of s times I 1 of s minus rho by s. In addition, you have a mutually induced voltage ms times the current in this coil. And what is the current in that coil? In a symmetrical way, you have I 2 of s here, this is V 2 of s, and you have another current source here which is rho 2 by s. So, the current in this coil is I 1 of s minus rho 1 by s, and the current here is I 2 of s minus rho 2 by s. So, now we see that this voltage V 1 of s is obtained as the drop in this inductor. What is the drop in this inductor due to self induced EMF? I 1 of s minus rho 1 of s times L 1 of s, and the mutually induced voltage is ms times the current here, which is I 2 s minus rho 2 by s. So, these are exactly the terms that we are having here. Similarly, the voltage induced in this, which is equal to V 2 of s, is the self induced voltage I 2 of s minus rho 2 by s times L 2 of s, and the mutually induced voltage which is ms times I1 of S minus rho 1 by S, that is the one. So, these are two alternative representations of the initial conditions in a mutual inductor. If you are in love with voltage sources, you use this diagram. If you like to use current sources, you can use this diagram. The advantage with the current source representation is that on one side you have only rho 1 only figures here, whereas here when you put the voltage source, both rho 1 and rho 2 come on both sides. That is a minor advantage. So, this is the way in which we can analyze the transient problems involving mutual inductances. Let us work out an example to clarify these ideas.